This talk is self-supervised learning and its application to human language processing. And before we start, this is an online lecture. So usually you do not know what a lecturer look like. So I show one of my photos. So this is what I look like. And this is me. And I wear a t-shirt with Sesame Street. And Sesame Street is highly related to self-supervised learning. So when you talk about self-supervised learning, you have to wear a t-shirt related to Sesame Street. And this is the outline of today's talk. There are two parts. So because this is a 2-hour lecture, so my plan is I give the part 1, then we take a 5 to 10 minutes break, and we have the part 2. So part 1 is the basic idea. I will introduce the basic idea of self-supervised learning. And in part 2, I will share you some of our recent study. So in part 1, I have to emphasize that this is not a survey. So as you know, because self-supervised learning is a very popular topic, so there are already many excellent survey papers. I list some of them here for your reference. Because there are already many good survey papers, so I'm not intending to survey this area again. So this lecture is for you to have the basic idea of self-supervised learning, but not try to cover everything in this research direction. And recently there's another survey paper called On the Opportunity and the Risk of Foundation Model. Foundation model here refer to self-supervised learning model, and it's a very long survey paper, more than 200 pages, and I do not really bother to count how many authors in this paper. So this is a very popular area, and already lots of the survey paper you can read. So let's start today's lecture. So in part 1, I will first give a very brief introduction about self-supervised learning. And I know when we talk about self-supervised learning, everyone have kind of different definition. So here, when I talk about self-supervised learning, what I actually try to refer to is pre-training. In the past, you only have 1-stage training. Now we have 2-stage training. Now it is very common to have 2-stage training. So you do pre-training first and have a pre-trained model. And there are different names for this pre-trained model. Some people call it foundation model. Some people call it upstream model, but they refer to the same thing. They refer to a pre-trained model. And this pre-trained model is task agnostic. We have this pre-trained model, but this model is not targeted at solving a specific task. It's task agnostic. And this model tries to develop general purpose to use in a large amount of downstream tasks. For example, if you are focused on natural language processing, then probably you want your pre-trained model to learn the meaning of words. So pre-trained model develop the general purpose of the knowledge it is needed for lots of different tasks. And in natural language processing, probably the pre-trained model learn the meaning of the words. Then you will use this pre-trained model in the downstream task. And we will talk about how to use the pre-trained model in the downstream task later. So one pre-trained model will be used in a wide variety of different tasks. For example, after you have a pre-trained model know the meaning of words, you can use it in summarization, you can use it in translation, you can use in question answering. So it has lots of different applications. So we have 2 stages of training. We have pre-trained, and the pre-trained model will be used in a set of downstream tasks. So what is the benefit for this self-supervised framework? The first benefit is this pre-trained model can be trained by a large amount of unlabeled data. It's relatively expensive to collect labeled data and relatively easier to collect unlabeled data. And usually this pre-trained model can be trained from a large amount of unlabeled data. For downstream tasks, because this pre-trained model already developed the general purpose knowledge from a large amount of unlabeled data. Now, in each downstream task, you only need very limited labeled data to fine-tune the pre-trained model to get good performance. So this is like, let me give you a metaphor here. So as you know today, if you want to develop an app on your cell phone, you will not do it from scratch. You develop the app based on an operating system. For example, you develop app based on Android. And so pre-trained model is something like an operating system. So the pre-trained model is developed for general purpose, and it can be used on a wide range of applications. So if you want to develop some machine learning application, you can take out a giant pre-trained model. You can take out your general pre-trained model and fine-tune it a little bit, and it can serve for different applications. So this is the benefit of self-supervised learning framework. So when we talk about self-supervised learning, I think the most well-known model is BERT. Besides BERT, there are a whole bunch of Sesame Street characters. For example, there is ELMO in natural language processing, is embedding from language models. And here there's BERT. BERT is bidirectional encoder representation from transformer. And there's ERNIE. So ERNIE is enhanced representation through knowledge integration. So I never know you can name your model in this way. They do not select the first character in a word. I never know you can name your model in this way. Then there is Big Bird. Big Bird is transformer for longer sequences. And it has nothing to do with Big Bird. They just directly name their model Big Bird. So in order to make their model in the Sesame Street. So you found that people like Sesame Street, they try to name their model based on the Sesame Street characters. And BERT is the most well-known one. When people think about BERT, usually you consider BERT as a giant, right? Like the giant in Attack on Titan, because it has large amount of parameter. BERT model has 340 millions of parameters. And here I know a secret I would like to share with you. But if you haven't watched Attack on Titan, this is a spoiler alert. So just close your eyes if you do not want to be spoiler alert. So the secret here is, if you have watched Attack on Titan, you know each giant are controlled by a human. Each giant has a human in it. And do you know who controls the biggest giant? Who controls the biggest giant? Bertolt Hoover is the one who controls the biggest giant. And it has the name BERT. It has B-E-R-T in its name. I believe this is not a coincidence. Don't worry if you do not get this joke. This is not important. And besides BERT, there are a large amount of giants in the world. So besides BERT, there are large amount of large model. Just like the end of the Attack on Titan, large of giant appear from the ground and is going to destroy the world. And BERT is not considered as a giant model anymore. So at the beginning, we have ELMO, 94 million parameter. Then we have BERT, 340 millions of parameter. It's developed in the end of 2018, 3 years before. So 3 years before, we think it's very large, but it is nothing today. For example, GPT-2 have 1,500 millions of parameters. So in the past, we think GPT-2 is very, very large, but today it's also nothing. Megatron is 8 times larger than GPT-2. T5 is 10 times larger than GPT-2. So Ford has one type of car called T5, but it's not related to the model here. T5 is trained by Google. And Turing NLG is 2 times larger than T5. But even Turing NLG cannot be considered as a big model today, because GPT-3 is 10 times larger than Turing analogy. So today, people like giant model. The model are become bigger and bigger. BERT is not considered as a big model anymore. So BERT, 340 millions of parameter. GPT-3, so which is trained in last year, 2020, is 175. It has 175 billions of parameter. So if we use the height to represent the number of the parameter, this is BERT, 1 millimeters high. Then this is me, and GPT-3 is Taipei 101 behind us. So this is to show that BERT and GPT-3, they have a very large different number of parameters. Today, those self-supervised models are truly very large. And actually, GPT-3 is not the largest one. Switch transformer have 1.6T parameter. It's nothing to do with Nintendo. It's also trained by Google. If you find any model which is larger than switch transformer, please let me know. So after the introduction, I will going to do some case. I will going to talk about BERT. So I will use BERT as a case study. There are a large amount of different types of self-supervised model, but I will introduce the most typical one, and hopefully you can get more idea about self-supervised learning. And I found someone have some question in the chat room. So let me check your question quickly. Okay, so I believe foundation model is just another name for pre-trained model. Is that correct? Okay, I have answered your question. And the next question is, can this principle be extended to other types of data? And can they only be used with attention type of network? Because BERT can do generation as well as classification with small multiplication, but ResNet could be hard pressed to generate images. Okay, so for your first question, so most of our example in this talk is based on natural language processing, but can this idea, pre-trained idea, be used in other types of data? The answer is yes. So it can be used in image processing. And in the end of this talk, hopefully we have time to talk about how to use the model in speech processing. So then your next question is, how can we use this model in generation? For ResNet, ResNet did not have, it's not easy to use ResNet as a generative model, but I believe this is depend on what is the network architecture of your pre-trained model. For example, it is also difficult to use BERT to generate sentences. BERT is an encoder, so it is not developed to generate sentences. If you want to do some downstream tasks which involve generation, so probably you want to use another model called BART. It's a pre-trained sequence-to-sequence model, so it has a decoder which can generate sentences. So I think this pre-trained idea is kind of very general. It is not limited to the architecture like BERT. You can pre-train your model on different types of architecture. If what you want to do is generation, then you can pre-train a model which is suitable for generation. Wow, a good question here. What is the difference between self-supervised learning and transfer learning? I know those buzzwords is all around you, so usually it's very hard for people to discriminate different terms. I would consider self-supervised learning as one type of transfer learning. So transfer learning is you learn from some task, and what you learn can transfer to other tasks. In self-supervised learning, you learn from some unlabeled data, then you can transfer to downstream tasks. So I would consider it as one type of transfer learning. But different from the typical transfer learning, today in self-supervised learning, we more focus on apply on a wide range of different tasks. So instead of just apply on one task, we hope that the knowledge learned from the pre-training can generalize to a wide variety of different tasks. can we build real-time application based on such giant model? You can do network compression. Although I'm not going to talk about this part, but you can find lots of people try to do network compression based on this giant model. So there are two research directions. One is make the model as large as possible. But on the other hand, there's a large amount of research try to compress the model. And all the technique you know about network compression have been applied on bird. So there are all types of bird. You can Google something like tiny bird, then you can find a lot of related research. The larger parameter always imply better performance. Since you highlight always, so it's not easy to answer this question. I'm not sure whether this is a theory to guarantee that larger model imply better performance, but based on the literature, there are so many evidence that larger self-supervised model can achieve better performance in the downstream test. We will show some results later. I found a question from Shen Tian. Do we really need those giant models for every research project? Given the huge cost for giant model, what suggestions can you give to poor students who do not have the computation budget? Yeah, this is something also I feel very worried because today for a speech lab, it is almost impossible for us to train a self-supervised model for ourselves. But on the other hand, I would consider those self-supervised model as an utility. They are something like Windows or something like Linux. So those models should be public available. So in the future, if we want to do some application, we can leverage those models to have better performance. So I would consider them like an operating system. I would consider them like a toolkit, and it should be something open and everyone can leverage them and try to get better results. So from this point of view, for example, you will not complain that those operating systems can only develop by large company because we can use those operating systems to do other things. So I will consider the self-supervised model as this operating system. We can leverage them to get better performance. So probably we cannot do research directly based on the operating system, but based on those giant model, but hopefully they can be helpful in the future. So I think what is important here is we need to force those big companies to open source what they train, because as you know, at the beginning, OpenAI, they do not want to open the GPT-3 model, but now they open their GPT-3 model as an online API. So it is possible to code the API and get the response from the GPT-3, and you can develop your application in this way. But but to get the API is still not very straightforward. But hopefully it can be more open in the future. Any similar large model for language other than English? Of course, yes. So there's Chinese bird, there is French bird. So there are all kinds of different language have their own bird model. The next question is, I have come across some research that larger model only use a part of their network to work. So the large number of parameters may be unnecessary. Yes, I'm talking about the lottery ticket hypothesis, but I may have misunderstood. I agree with you. So there's lots of research show that you can prune your network to be very small, probably only 5 or 10% of the original network and get the same performance. So this is why network compression is possible. So as you know, there are lots of giant model, and if you want to use it on the edge device, it is almost impossible. So there's also lots of work trying to compress them. And those typical ideas about network pruning, knowledge distillation, they work well on they also work well on compressing the self-supervised learning. Here's another question. Does it mean that while GPT might be impossible to train by an individual or lab, it can be leveraged by us? Yes, this is what I mean. But how to leverage? Would you be able to fine-tune this model, and therefore is the leverage, or can we compare output GPT-3 to our own model? This is a very good question. Because GPT-3 is so large, even though OpenAI want to share the model, you cannot fine-tune it. Probably you cannot even download the model because it's so large. So there is a new search direction called prompting. That is, consider GPT-3 as an online API. We can do nothing about it. We can only give it some input and it outputs something. Then how can we use this model? How can we use GPT-3 in this way? This is called prompting. Hopefully we have time to talk about it. Okay, so do I miss some question here? So you are saying that pre-training model like public resource. Yes, I believe those pre-trained model should be something like public resource. Or even though the big company want to charge us a little bit, not too expensive, which is probably acceptable. It should be something like, for example, you still need to pay some money to buy Windows or buy Office or Excel, but it is very easy to obtain this toolkit. I believe those self-supervised models should be the toolkit everyone can leverage. Is it possible to a universal algorithm for parameter compression? I do not really get what do you mean by universal algorithm. There are large amount of different algorithms, for example, pruning, distillation, parameter quantization, and spatial network design. And usually they are not conflict to each other. You can apply all the algorithms at the same time and try to make your model at the smallest. Yeah. Just a thought, would it be possible to use compressed setting to prune the model? I believe this is one way you can do that. So, but I have to admit that I'm not the expert of compressed sensing. So probably we can leave this question for the future discussion. Okay, so thank you very much for all the questions. I'm a little bit surprised how excited you are, how many questions we have here. So thank you very much for all the good questions. Thank you. So let's continue. So I'm going to talk about BERT. Okay, let me turn to the next page. Okay, so I have introduced the framework of self-supervised learning. And the first stage in self-supervised learning framework is pre-training. So how does BERT do the pre-training? The first thing you have to know that is BERT is for natural language processing. So it's trained from text. It's trained from a large amount of unlabeled text. And I know not all of you is working on natural language processing. So I have to introduce a little bit about how a model process and sentence. So given a sentence, the first thing you do is you will tokenize the sentence. So given a sentence, you will split the sentence into a sequence of tokens. But there are different ways to define what is the token in a sentence. One very typical way is consider each word as the token. For example, given the sentence One Punch Man, it can be split into 3 tokens. But not all the language can use this way. English, probably word is a suitable suitable token. But for some language like Chinese, there's no explicit boundary between the word. So word is difficult to be defined in Chinese. So word is one type of possible token. Another possible choice is grapheme. Why is grapheme? Grapheme is the smallest unit of a writing system. For example, you can consider English alphabets as grapheme. For example, given the sentence One Punch Man, O is a token, N is the second token, E is the third token. You should also consider space as a token, then P is another token, and so on. Grapheme is another choice. But in BERT, they choose something like morphine as the unit of token. What is morphine? Morphine is the smallest meaningful unit. It's larger than character, but small than word. For example, unbreakable can be split into 3 morphemes. Unbreakable can be considered as un, break, and able. So unbreakable is composed by 3 morphemes. And usually a morpheme has some specific meaning. So even though there's a new word, you can guess the meaning of the word based on the morphemes in the word. For example, given a sentence or given a word rekillable, it is composed by 3 morphemes, re, kill, and able. Although probably you have never seen this word before, you can guess its meaning. So rekillable is probably someone like Kenny, who is die in each episode, but bring to the life every time. And how can we get morphemes in a language? There are 2 different ways. One is find a linguistic to tell you what a morpheme is in a language. Another way is data-driven. There are data-driven approach to find morpheme from a language. And BERT use the data-driven approach. The data-driven approach used in BERT is called BPE, by pair encoding. I'm not going to go through the details of BPE. I just want to let you know that the input of BERT is a sequence of tokens. So it's something like this. It's something like the token I showed here. So the input of BERT is a sequence of tokens. Let's get down to the business to talk about how BERT is trained. So BERT is mainly trained by masking the input. So this is BERT. It is actually a transformer encoder. And you random sample a sentence from your data set. Those sentences do not have to be labeled, just random sample some sentences. Then you will mask some tokens in the sentences. How do we mask the token? For masking, I mean you will replace a word, or actually a token. You will replace a token with a special token. This special token represents masking. There's another way to do the masking. That is, you random replace a token with another token. So you have 2 ways to do the masking, and when training the BERT, both ways are used. Then you input a sentence, and there's some token being masked in the sentence. Then BERT will output a sequence of representation. Then there's a linear model, there's a linear layer. This linear layer tries to predict the mask token. So it have to, so the input sentence is, how are you today? And the token R is being masked. So the model have to predict R. So the linear model have to predict the mask token is R based on the output representation here. So this is the basic idea of masking input. And it is very trivial to train this network because you already know the ground truth. You are the one who do the masking. So you know what is the original, you know what is the original token being masked. So during the training time, what you have to do is you have to train this linear model and this BERT model. They have to be trained together to predict that the masked word is R. I found a question here. So the question is, what are the advantage of using subword token over whole word and character level token? So when you use the whole word as your token, there's the problem is it is hard to enumerate all the possible words. For example, in English, there are at least more than probably 100,000 of different words, and there are new words invented every day. And in Chinese, it is almost impossible to enumerate all the words. You can always compose some character to invent a new word. So if you use word as the input, then the problem is you cannot enumerate all the words. So you will not use word as your token. For character, you can use character as the input. It depends on which language you are considered. In English, because character is a very small unit, English alphabet is a very small unit, it do not really contain much information. So if you consider English alphabet as your unit and you simply mask one alphabet, it's very easy for your model to predict what is masked. Then it probably learn nothing. For Chinese Chinese character usually have some specific meaning. So in Chinese, you can use character as your token. Actually, in BERT, when the BERT apply on Chinese, usually Chinese character is considered as the token. But the English, they use morphine. Is the primary output of BERT and embedding? Yes, BERT output embedding. Probably the size of converted sequence. Yes, this is also a good point. So if you consider character as your unit in English, then the sequence will be very lengthy. And as you know, so BERT is a transformer model. So there are self-attention in the transformer model. And the complexity is length, the length square is the square of length. So if your length is too long, it's very difficult to train a transformer model. Actually, the input of BERT is only 512 token. It's hard to train a BERT with longer input. Okay, so Arrow Kumar as the mass word prediction cross entropy is across all possible words in the dictionary or specific corpus. It is across all possible words in the dictionary. So it's very large. And there's some way to deal with this problem. For sequence classification with long text, what kind of model do you recommend? Because 512 max length of BERT is a limitation. Yes, it depends on your application. I'm mainly working on speech. In speech, we also train speech version of BERT. And if this is the case, if speech is the input, our input sequence is usually much, much longer than text, much, much longer than 512. So usually you need some special architecture. You cannot use typical transformer. You know, there are all kinds of different favor of self-attention. And there are something like reformer or performers, and there are many different ways to reduce the computation of self-attention. So if you want to do that, if you want to take care of a very long sequence, there's some way to do it. how word piece work. Okay, if we have time, we can talk about that in the end. Okay. How to handle the long input. Okay, since this question appeared twice, so probably I can explain more. You can Google something called long range arena. Arena is the place you fight each other. So you Google long range arena is a benchmark corpus to deal with extremely long sequences, and lots of different models already apply on it. So you can go through the model, apply on long range arena, and see their performance and choose the one you want to use. I hope this is helpful for you guys. Okay, thank you. Thank you for your question. Yes, if possible, someone please type that out. Long range arena. Arena is somewhere you fight to each other. Okay. Yes, good. So let's continue. And besides masking the input, BERT has another objective function, which is next sentence prediction. So you will train your BERT in this way. Now your model take 2 sentences, and there is a special token to separate the 2 sentences. And in front of the 2 sentences, there is a special token called CLS token. CLS token represents the whole sentences. Then from the position of CLS token, there is an embedding. Then there's the linear model, take the embedding here as input and output yes and no. So if these 2 sentences are consecutive sentences, then the output should be yes. If these 2 sentences are not consecutive, they are independent from 2 different documents, then the answer should be no. Then you train your BERT in this way. This approach actually is not helpful. So in a paper called ROBERTA, Robustly Optimized BERT Approach, it shows that actually next sentence prediction do not improve the performance. However, there's another version of sentence prediction. We try to predict the order of 2 sentences, which is shortened as SOP, is used in another model called Hilbert. It seems to be helpful in Hilbert. So this is another objective that you train your BERT. Yes, so that's all about pre-training. Very simple, right? Then let's get down to the downstream task to see how the BERT model is used in the downstream task. And in natural language processing, you can use your BERT in 4 different ways. Let's quickly go through the 4 different ways. So in the first case, the input is a sequence, the output is a class. For example, what you want to do is sentiment analysis. So the input is a sentence. For example, this is good. And the output should be this sentence is positive or negative. Then your BERT will take this sentence as input. Then from the position of CLS token, it output an embedding. And this embedding will be the input of a linear model, and linear model should output the classification result. And linear model plus the BERT model is the whole model you use during the classification. And for the BERT model, for the linear model, you do random initialize. And for BERT model, you use the pre-trained version. You use the pre-trained model to initialize your model here. So BERT is already pre-trained by masking the input and next sentence prediction. And you use this model as the initialization parameter when you training your classifier. And why we want to use the pre-trained model? The simple answer is it's better than random initialize. And there is so many strong evidence that pre-trained model outperform random initialize or train from scratch. Here is just a typical result from the literature. So here we have different tasks, different color represent different tasks. doesn't matter what the task really is. And the horizontal axis is the training epochs, and the vertical axis is training loss. And here for each color, there are two types of line. The line, the one with dots, the dotted line represent train from scratch. And another type of line represent fine-tuning, means your model is pre-trained. So you can find that, let's say we compare the green dotted line and this green line. You can find that if you train from scratch, actually it's very hard for the loss to be lower. On the other hand, if you train from pre-training, so you do not train from scratch, you already pre-train your model, it's easier to make the loss lower. So there's lots of benefit if you pre-train your model. Then for the second case, in the second case, the input is a sequence. The output is each token in the sequence will obtain a label. To be more specific, here I take POS tagging as an example. You have to know the POS tag of each word. So given a sentence, I saw a saw, the machine have to know that the first token is a noun. The second one, this saw, is a verb. And the last saw, the second saw, is actually a noun. So this is POS tagging. So how Bird deal with this POS tagging? What you do is like this. Bird will take a sentence as input, and it output a representation for each token. And each token will be the input of a linear model, and we will output a class. Okay, so we will output a class. So each token will obtain a class. Then you train the linear model here and the bird model jointly. Then you can do POS tagging or other similar tasks. This is case 2. For case 3, some NLP application need to take 2 sentences as input and output a class. For example, natural language inference. In natural language inference, you have a premise, you have a hypothesis, and your model have to determine, given the premise and the hypothesis, are they contradiction, or are they entailment, or they are neutral. For this type of NLP task, you can use your bird in this way. Bird can also take 2 sentences as input. So you give it 2 sentences, use a separate token to separate the 2 sentences, and put a CLS token here. And here you will take the embedding of CLS token as the input of a linear model, and hopefully linear model can output the correct class. And you will train the linear model and the bird model jointly for, like, for example, for natural language inference. This is case 3. For case 4 is widely applied, but a little bit tricky. So in NLP community, extraction-based question answering has been widely studied. So what is extraction-based question answering? In extraction-based question answering, your model read a document and it read a question, then it has to output an answer. But we assume that the answer is always in the document. So if the answer is gravity, you can find the center, you can find gravity in the document. Or your answer is within the cloud, you can find within the cloud in your document, and so on. To solve this task, a typical idea is train a question answering model, input your document, input your question, then simply output 2 integers. For example, if let's say gravity is the 17th token in the document. So if you want to output the answer gravity, then you have to output 2 integers, 17 and 17. So after you obtain this 2 integers, you can look up the terms, you can look up the tokens in the document and find that the 17th token is the answer. Or for another example, if the answer is within the token and within is the 77th token and cloud is the 79th token, then your model have to output 77 and 79. Then it will obtain the correct answer. This sounds like a little bit tricky. The first time I heard that people use this idea to solve expression-based question answering, I don't believe this kind of model will work. But actually, it is very common today. Today, when people talk about expression-based question answering, we usually solve it by this approach. And how can BERT use in this scenario? So you use BERT in this way. So the BERT take question and document as input. Then there is two vectors. These two vectors are the parameter you have to learn. They are random initialized. You use the first one to compute the inner product with all the embedding in the document. And the result of inner product will determine the start position of the answer. So let's say that in this example, the second embedding obtain the largest inner product with this orange vector. Then the start token, then the start position will be 2. On the other hand, you will use this blue one to compute the similarity. You will use this blue one to compute the similarity with the embedding at each position. Then you obtain the result of inner product, and you find that the third embedding has the largest inner product with this blue vector. Then the third position will be the end of the answer. So we know the beginning of the answer is at the second position, and the end of the answer is at the third position. So you know that the answer is D2 and D3. The second token and the third token is the answer in the document. I know this sounds pretty amazing. If this is the first time you see this kind of model, I think you will not believe it will work, but it works anyway. What happens if E smaller than S? Okay, so if E smaller than S, you can say that, well, there's no answer. It is possible that some question is unanswerable. So in the benchmark corpus, there is some unanswerable question, and the model have to say unknown to get the correct answer. Oh. Yes, there's a question that are all these 4 cases supervised and hence require labeling? Yes, the 4 cases are supervised. We use unlabeled data to train BERT, so the process of BERT training is unsupervised. But when we use BERT in the downstream test, here we have 4 cases, they are supervised. How would BERT be used for summarization? So I know why you asked this question, because BERT cannot generate sentence, so it cannot be used in summarization. We will see another model probably more suitable for summarization later. I guess those 4 cases are pre-text test before the down. Oh, no. Yes, then those 4 cases are not pre-text. Mask input and next sentence prediction are pre-text tasks, and those 4 cases are downstream tasks. So all the possible downstream tasks in natural languages are separated into 4 different cases, and hopefully BERT can solve most of the natural language processing. But as I have mentioned, if you need to generate a sentence, BERT cannot do that. There are more general models which is more suitable for generation. But D2 and D3 were different documents. How is the answer? Oh, sorry, I do not express it in a clear enough way. The whole document has 3 tokens, D1, D2, D3. Okay, so D2 is the second token in the document, D3 is the third token in the document. Yeah, I hope I answered below Lena's question. So okay, you say got it. Okay, thank you. Okay, so this is all about the downstream task. And today, if you want to test the performance of self-supervised model, you would not just use one task. Because self-supervised model, those pre-trained model are trained for a wide range of different tasks. So usually you will evaluate the pre-trained model on many different tasks. A very typical way in natural language processing is use GLUE. So there's the benchmark corpus called General Language Understanding Evaluation, or GLUE, and it includes 9 tasks in GLUE. And when you have a new pre-trained model, usually you will evaluate the pre-trained model on those 9 downstream tasks. Then you average the performance of the 9 downstream tasks to get something called GLUE score, and you use this score to claim that you are state of the art. Okay, so this is GLUE score. This is the result of the performance of all different kinds of model on GLUE, and each point here represent a task. Different colors of point represent different tasks, and each column is a model. You can find that all of them are pre-trained model. So you found bird and lots of different variants here. And what is the black line here? The black line here is the performance of human being. Okay, so this line represents the performance of human being. And the blue line is the average GLUE score, is the average of the different tasks. It averages the evaluation metrics of different tasks. And you can find that there are some models eventually outperform the GLUE score of human being. So it looks like, well, those self-supervised models are already pretty overfit on the GLUE task. So people invent super GLUE, which is another even more difficult task. So anyway, I show this benchmark corpus result to let you know that today, if you want to evaluate a pre-trained model, you will not just do one task. You will do a set of tasks and average their performance and tell people that you are the state of the art. Okay. Okay, so why does BERT work? A very typical answer. I will provide a typical answer first, and in the second part, I will show you another result. And the typical answer is BERT is something very similar to word embedding. In the ancient time, I mean, probably around 10 years before, lots of people working on word embedding. Word embedding means you want to represent a word by a continuous vector. And this vector include the meaning of the word. So for example, the embedding of tree will be close to flower. The embedding of dog should be close to cat, something like that. So this is word embedding. Then how do people train word embedding? A representative way is called SIBO. I know there are lots of different ways, GLOVE, skitran, but one representative way is SIBO. And you can find that the training of SIBO is very similar to BERT model. How does the SIBO train? SIBO train in this way. So given a word sequence and you mask the one token and you use the neighbor token to predict the mask token. So this is SIBO. And SIBO is a very simple model. It only has 2 linear transformations, but it tries to use the context to predict the mask token. And this is very similar to what does BERT train, right? And this is basically the idea from linguistic John Robert Firth. He say you should know a word by the company it keeps. So you can know what is the meaning of word by its label. So when you use the label from its neighbor, so if you use the neighboring tokens to predict the mask token, you can get the meaning of a specific token in this way. This is typical word embedding. Compare with BERT. This is just how BERT is trained, right? So BERT is a larger version of SIBO. SIBO just two layers. And actually both the layers are linear layer. It does not have activation function. So it's just a linear transform. In BERT, you have 12 layer, 24 layer, 48 layer. You use a very sophisticated model to predict the mass token from its context. And in SIBO, all the word will only have a specific representation. But in BERT, the representation is depend on the context. So given the same words, if the context is different, then the representation will be different. So BERT is not only word embedding, it's contextualized word embedding. To be more specific, here is the BERT. You give it a sentence, and each token will have a representation. This representation represents the meaning of a specific token. And this representation depends on the context. Even though you give BERT the same token, if the context is different, then the representation will be different. For example, the term apple, the token apple, may have different representation. If the apple is after the word eat, it will have the embedding probably close to orange, because in here, apple means something you can eat. Then so it's one type of fruit, so it's close to orange. For Apple Watch, it's not something you can eat anymore. And probably when Apple is concatenated with the word watch, its embedding will close to computer. So this is the idea of contextualized embedding. How is the final embedding converted back into a token? So I think what your question is, here the BERT output a set of embedding. Then during the training time, during the pre-training, you have to use this embedding to predict the token. So how can we do that? So the idea is you apply a linear transformation. So it's like a linear classifier. You use the representation as the input of the linear classifier, and you consider each token as a class. Could you please give an intuition of how BERT managed to give a contextualized embedding? Let me try to be more specific. So here we have a term learning, right? So you input a sentence, Asia Machine Learning School, then it output a set of representation. But what would happen if we change the context of learning? The representation will change, right? Because the model is a transformer. Transformer have self-attention layer, and the self-attention layer will consider the whole sentences. So even though there's only one token, which is different in the sentence, the output token will be completely different, because your BERT model, your self-attention layer, consider the whole input sentence. So even though the learning, the learning here is the same, but you change one word here, for example, you change Asia into Europe, then the representation here will be completely different. So this is why I say BERT embedding is contextualized. Even though this embedding corresponding to the same token, if the sentence is different, then the output representation is different. Yes, but this is just one way to explain why BERT works. I will show other experiments to make you rethink why BERT is work. Wow, it's already 3 o'clock. Time flies. Okay, so probably I can skip a few pages here. So this page is nothing. I just want to share with you that it is possible to train a BERT by yourself, but it takes time and some money. Yes, yes. So if there are 30,000 tokens, wow, your linear layer has 30,000 parameters. So linear layer can be very huge when you have a large amount of tokens. Yes. I would like to skip a few pages. Okay, so let's briefly talk about pre-training. So we already give a case study about BERT, but there are all other pre-training approaches. So let me quickly go through it. I would like to skip a few pages and directly talk about something you will be interested in. There's another question. Any scope of lottery ticket hypothesis here? Unfortunately, no, I'm not going to talk about lottery ticket hypothesis here today. But the lottery ticket hypothesis has also been verified on BERT model. I believe you can just Google with something like lottery ticket hypothesis plus BERT, and you can find the result of lottery ticket hypothesis on BERT. So the hypothesis also works on BERT. But we will not talk about parameter reduction today. Yes, and I missed a question. Someone asked, does that make softmax and cross entropy ineffective? Yes, and this model, the model on the slide, is going to solve it. Okay, so I know you are very worried that if we have 30,000 tokens or even more, does that mean we have a very giant linear layer? So it will be problematic to train this large linear model. Yes, it's problematic. So there's another way to train BERT, which is called Electra. Electra is effectively learning an encoder that classifies token replacements accurately. People are very good at naming their models today. Okay, so in Electra, we are not going to predict the token anymore because predict token is something very computationally intensive. So in Electra, what it actually wants the model to do is the model have to detect whether a token is replaced or not. What do I mean by that? So given a sentence, the chef cooked the meal, and you replace the cook with at, and you also output representation. Now the model have to predict, given the representation, the token is the original token or it has been replaced secretly. So if the token is being replaced, the model have to output yes. And this is simply a binary classification, right? So it is not a multi-class classification. You do not have to worry about a very large linear layer anymore. Your model will become much smaller. You only have to do binary classification here. Okay, the problem here is, how can we replace a token here? If we simply random replace the token, the task would be too simple and your model will not learn meaningful representation. So what it actually do here is the offer of Electra, they train a small BERT, and this small BERT can put a mask here and output a prediction. And they replace the original token by the predicted result. And they train another model, which is going to be truly used in the downstream task. They train another model to determine this token has been replaced or not. And but I have to mention that this is not GAN, this is not discriminator, this is not the generator, because they do not train iteratively. So it is still a little bit different from GAN. And this is the result of Electra. We can take a look at the figure at the right-hand side. And you can find that the horizontal axis is pre-trained fluff. So how many computation you need. And the horizontal axis is the glue score, the larger, the better. And you can find that some model like XLN, they can get very good performance, but with a large amount of pre-training. For Electra, you need much less pre-training to get similar performance. So if you are worried about a very large linear model, then Electra is your friend. And I like to skip this one. This is how you train GPT, but it's just a language model, so probably I can skip this one. Okay, let's talk about this one. Then some people are worried that you talk about 4 cases for using BERT, but it do not cover all the cases, right? There are a lot of cases which cannot be included in the 4 cases. Yes, you are right. For example, some students already talk about summarization. So, well, it's not easy, it's not trivial to use BERT in summarization. Then there's another even more general way to pre-train a model. In BERT, we only pre-train an encoder. Now, how about we pre-train a sequence-to-sequence model, include an encoder and a decoder? Then I found a question here. Sorry, I don't understand how this reduces the problem of 30K parameter. Okay, so I think you refer to Electra. So here, yes. So here, in the original BERT, let's not talk about Electra. In the original BERT, you have to predict each embedding is from which token. And let's say there are 30,000 tokens in the world. Then what is the model you need to predict 30,000 tokens? Let's say this embedding is, for example, its dimension is 500. Then if you want to predict 30,000 tokens, then your transformation will be 100 times 30,000, right? It's a very large number. But on the other hand, if what you want to do here is a binary classification, the output is only yes or no, not the whole lexicon, not the whole token set, just yes or no. Then let's say the embedding is 500, then the parameter you need is 500 times 2. But actually, it's a binary classification. So not 500 times 2, actually only need 500 times 1. But now we need to do check for every token in sequence. Yes, and yes. Now, in the original BERT, you only worry about the mask part, but now you are going to consider all the position. However, this will make this process consider all the token is another benefit of Electra, because you can fully leverage all the computation. So in the original BERT, you only consider one specific position. However, to consider one specific position, you have to consider the whole alternate. Now in Electra, you consider whole alternate, but all the position will be used in prediction. So actually, Electra is more effective compared with BERT. I hope this answers your question. So let's talk about sequence-to-sequence model. So you can pre-train a sequence-to-sequence model. Then how to pre-train the sequence-to-sequence model? The idea is very similar to BERT. What you actually do is you will corrupt the input sentence, and your encoder take the corrupted sentence as input, and your decoder have to reconstruct the original sentence. And for corruption, how to corrupt the input sequence, there are many different ways. One way is just like BERT, mask some of your token. This is used in a model called mask. Then there are other ways. You can delete some token. You can permute the input sequence. You can do the rotation. You can do text infilling. Text infilling means you will insert some mask, but those masks do not corresponding to any token. So model has to know that this mask is fake. Between A and B, there's no extra token. So your model has to know that this mask is fake and just delete it. And use all the method together, you have BART. This is another self-supervised model widely applied. And it is not a Sesame Street character anymore. I don't know why they do not find a Sesame Street character now. And so if you want to consider something like summarization, probably you would choose to use BART instead of BERT. Okay. And probably you would ask, there are many different ways to corrupt the input sentence. Which one is most effective to train the sequence to sequence model? Google already addressed this question. They have T5. In T5, they try all the different corruption approach. They already enumerate all the hyperparameter, and they have a very long paper, more than 50 pages, and you can directly read the conclusion. They will tell you which way is most effective. And they also have a very giant corpus called Colossal Clean Crawled Corpus, which is abbreviated as C4. And this is a very giant corpus. It has 7 terabytes, and it's even hard to process by yourself. When you download the corpus, and the web page will warn you that if you just use one CPU to process the corpus, it will take 1 year to process the corpus. So, okay, we can skip this page. And actually, besides BERT and BAR and T5, self-supervised learning also apply on image. And on image, it is another story. Due to time limitation, I do not intend to go through this part. I just want to tell you that on image, well, it's another whole brand new story, probably another 2-hour tutorial to cover it. So there are a large amount of different types of model. Okay, so then let's quickly talk about how to leverage the model in the downstream test. This is very important for you because, as you know, as a student, you cannot train this kind of giant model, but we can learn how to leverage those giant models. And the most common way is fine-tuning. So fine-tuning means for each different task, you will fine-tune the model by some task-specific label data. So for task 1, your model will be fine-tuned. For task 2, you have another fine-tuned BERT. For task 3, you have another fine-tuned BERT. If you have 100 tasks, then you have 100 different fine-tuned models. But in this way, if you want to solve all the 100 tasks, you have to store 100 different BERTs. It costs a lot of memory. Probably is not very efficient to do that. Another way to leverage this kind of pre-trained model is consider the pre-trained model as feature extractor. So pre-trained model output the representation and directly use the representation as the new feature for your downstream task. But usually this way is not very effective because if you only pick the last layer, usually the last layer is not the most informative layer. Some middle layer probably include the information you want. So, but which layer should be chosen? There's no trivial solution. So one way is use the weighted feature. And this idea is used in Elmo. So in your whole model, there are many different layers. You do not know which layer should be used. You do not know the output of which layer should be used. Then how about use all of them? You just do the weighted sum of the feature from all the layers. So for the embedding in layer 1, weighted by W1. For the embedding in layer 2, weighted by W2. And sum them all together, then you get a new representation, and this new presentation will be the input of your downstream task. And how we assign the weights here, those weights are learned with the downstream task. So those weights can be considered part of the downstream model, and you will learn the weights with the downstream task. So for different tasks, you will have different weights. No, I do not mean concatenate. I mean sum them together. You can also try concatenation, but what I'm worried here is if you concatenate all the features, it will be very lengthy. Okay, so usually your model is very large, have 20 layers. Yes, I think you got the idea. Yes, so it is average here. Okay, another way is adapter. So adapter means you insert a small module into your giant bird. Then during the fine-tuning stage, we will fix most parameters in the bird, and we only fine-tune the adapter. So most parameters in the bird model will keep the same, and only the adapter module is different for different tasks. So if you want to use bird in 100 different tasks, you do not have to store 100 birds. You only have to store one model and 100 different adapters. And usually adapters is very small, so it's fine to have 100 different adapters. To be more specific, people add adapter in this way. This is just the most naive one. There are so many different ways to use the adapter. This is still a problem under investigation. So one of the very typical way to use the adapter is in this way. You insert adapter after the feed-forward layer. And in each adapter, it's just a small network with 2 layers. So, and only the parameter in the adapter will be fine-tuned during the downstream task, and all the other parameters will be fixed. Okay, let's talk about prompting. Today, the pre-trained model can be so large. For example, GPT-3 is so large that you cannot even download it. It's just an API online. Then how can we leverage those giant models? So people are considered one way called prompting. Although prompting is originally designed for GPT series, here I use BERT as an example because we do not really talk about GPT in today's lecture. So you use prompting in this way. So you will always fit your pre-trained model. It's just an online API. You cannot change it. There's nothing you can do about this pre-trained model. You can only give it some input, and hopefully you give you some output you want. So you use your pre-trained model in this way. It will take a description as input, and let's say you are considering sentiment analysis. Then your description will be like this. This task is sentiment analysis. Hopefully, pre-trained model can understand this sentence. Then you have training example to show your pre-trained model what sentiment analysis look like. So your training example is something like that. I'm good is positive. It is bad is negative. Then you provide your model testing example. He is nice is, but we do not know the answer. And you put a mask after your testing example. And you know, BERT will try to predict the mask token, right? So BERT will say, probably the word mask here is, oh, I do something wrong. This should not be negative. The correct answer should be positive. So if your pre-trained model answer negative, then this is not a correct answer because he is nice is a positive sentence. So hopefully pre-trained model will say the token mask here is positive. And if it output negative, it cannot be considered as a correct answer. So I know this sounds very amazing. Can pre-trained model really work well in this way? It doesn't really work. So you can read the paper about prompting, especially the earliest one, for example, GPT-3. this approach do not really give us good performance. But surprisingly, it works on some tasks. But this idea, this research direction is attractive because in this way, the pre-trained model can be always fixed. Don't worry about fine-tuning, or even don't worry about download the model. It can just be an online API. Then the research question becomes, we cannot tune the pre-trained model, but how can we design the prompting here? How can we properly describe the task? How can we properly arrange the training example? And hopefully the model can give us correct result. This is prompting. Then the next question is, can we train the prompting here? Can we train the description? Can we train how to arrange the example? Yes. And this research direction is called prompt tuning. You can use this keyword to search large amount of paper. But we have a question here. Is adapter virgin BERT more preferable than fine-tune whole BERT? How about only fine-tune, less few, 1 or 2 layers of BERT? Is it preferred? Which fine-tuning method is more preferable? First of all, we have to clarify, what do you mean by preferable? If what you mean is performance, if accuracy is the only thing you care, fine-tuning usually obtain the best performance. But if you only have a very limited data, sometimes prompt tuning or adapter can outperform fine-tuning the whole model. But if in a specific downstream test you have sufficient data, fine-tuning usually gives you the best performance. But why we consider adapter? We consider adapter because we do not want to have a fine-tuned model for all the different tasks. We only want to have a fine-tuned adapter for all the different tasks. Then I think your next question is, why we add the adapter? Why don't we just say we train the first few layers of BERT or last few layers of BERT? We insert an extra adapter because we do not want to change the original parameter of BERT. We want to keep the BERT in its original shape. We do not change it anymore. We just plug in another extra parameter. Yes, so it is basically compute constraint. Yes, adapter is something. Some adapter is developed because compute constraint and memory constraint. It is not developed to achieve better performance. And here we have some result. You can check this paper for more details. So here the horizontal axis is modeled with different numbers of parameter. The vertical axis is superglue score. I have mentioned that glue is too simple today, so people working on superglue. And if you simply do model tuning, you get the red and orange line, orange curve. They are actually pretty good. And if you simply do prompt design, you use some prompt and design by human handcrafted prompt. Actually, they do not work. So as I have mentioned, prompt do not really work well. It's just a fancy idea. It do not really work well. But if you use prompt tuning, means your prompt is learned from the data. It's not handcrafted. It's learned from the downstream task. Then if your model is big enough, you can get the performance as good as tuning the whole model. So the prompt tuning is the green line here. But if you only have little parameter, you have less parameter, its performance not as good as model tuning. So as I have mentioned, model tuning can give you the best performance, but the prompt-based approach, adapter approach, is for computing resource and memory constraint. Okay, so this is for the first part. So let's not take a break, okay? Because we only have 30 minutes. So let's not take break, directly go to the second part. And you can ask question whenever you want. You can type in the chat room. I can see it. I can see the question. So let's move to the second part. Okay. I will talk about some interesting fact about BERT or other self-supervised model to blow your mind. Okay. So the first finding is about the cross-lingual capability of BERT. So there's a model called Multilingual BERT. It's trained from many different languages. So multilingual BERT, you use English sentences to train it. You also use Chinese to train it. Actually, the public available multilingual BERT, which is released by Google, is trained from more than 100 different languages. So what can we do with this multilingual BERT? Surprisingly, it can do zero-shot reading comprehension. That is, in the downstream task, you train the multilingual BERT with English question answering data. Then it can directly answer the question of Chinese. So do you get this scenario? Our testing data is Chinese question answering data set. But during the training time, we do not have any Chinese question answering data. We train the multilingual BERT with English question answering training data in the downstream task. Then the model can directly apply on Chinese question answering data set. This is very surprising when I first see this result. Here is some specific value. So here our testing data is DRCD, is a Chinese reading comprehension data set. And our English training data is SQUA. Then if you use QANet, which is not pre-trained, and you directly train the QANet on Chinese data, you get F1 score like 78. So it's fine you do not know what is F1 score, just consider it as accuracy. And for BERT, if you use Chinese version of BERT, their Chinese version of BERT, and fine-tune it on Chinese reading comprehension dataset, and test it on Chinese reading comprehension dataset, you get 89% F1 score. Actually, human only obtain 93% F1 score on the same corpus. So this is a pretty good performance. But what made me surprised is if you have a multilingual BERT trained from more than 100 languages, then you fine-tune the BERT with English reading comprehension dataset. Then evaluate your model on Chinese reading comprehension dataset. Then you get 78% F1 score, as good as QANet without pre-training. So this is something very surprising. Okay, I see some question here. Does it imply that Amber can handle code switching data very well intrinsically? This is a very good question. You can read our paper here. I put a link here. We do try to evaluate the model on code switching data set. And actually it worked well, even though the sentence is code switching and it has never read code switching sentence before, it can still get the correct answer. So it looks like multilingual BERT can handle code switching data. What is code switching data? Oh, it means you have more than one language in a sentence. Oh, yes, someone have answered the question? Okay. We do a lot of different experiments to verify this cross-lingual transferability. You can read our paper to learn more. I just show one table here. And we are not alone. Lots of people already also find this observation almost at the same time. So this is a very general cases. On lots of different tests, lots of different language pair, you find this cross-lingual transferability. And now there is actually a benchmark corpus to evaluate the cross-lingual transferability of your pre-trained model, which is called Extreme. In Extreme, you have to train your model on English and apply on another 40 different languages. And why multilingual bird can achieve this kind of cross-lingual capability? One intuitive idea is it can do cross-lingual alignment. That is, when multilingual bird take Chinese and English as input, it does not consider Chinese and English as different languages. It will map the token from different language, but the same meaning together. So if you understand Chinese, this is rabbit, and this is the Chinese character of rabbit. And if you analyze the representation of multilingual bird, you will find that different token from different language with the same meaning will be surprisingly aligned together. So when you train a multilingual bird, it automatically learns this kind of capability. I have a question here. Is the token list in multilingual bird include both Chinese and English token? Yes, it includes both the Chinese and English token, and actually it includes the token of 100 different languages. So it has a large token size, but actually, to my best knowledge, its token size is just around 30,000, and probably 30,000 token can cover all the token in different languages because lots of different languages share the same sets of tokens. Here's a general question. Can we use bird for fake news? Okay, so to answer this question, the keyword is Grover. Grover is also another character of Sesame Street. You Google Grover, Gravor, if I spell correctly, and the paper will answer your question. Does multilingual bird has more parameter than the standard bird? No, they use the same architecture. So it does not really have more parameter. You may try Roberta if you want more parameter. Yes. Grover. Okay, someone type it for me. Okay, so this is cross-lingual alignment. Then my question is, what is the factor influence the cross-lingual alignment? So there's some way to evaluate how good the alignment is. I'm not going to go through the detail here. So you just know that the larger the value here means the two languages are aligned better. So here we consider the alignment between, for example, English and French, and English and another different languages. And the blue bar is Google's multilingual bird. It achieved very good alignment. Then we try to train multilingual bird ourselves. We use 200,000 sentences for 10 different languages. So we train a multilingual bird with 10 different languages, but the result is pretty poor. We do not observe the alignment from our pre-trained model. Then what happened here? So my students spend a lot of time, fine-tune all different hyperparameters. So when you're working on machine learning, you are especially deep learning, usually you have to search the hyperparameter, waste a lot of time and money, search for the hyperparameter, but we cannot make our multilingual bird work. Then one day we think, is it possible that we do not use sufficient data? How about we use 1 million of sentences for each language? It may take a lot of time to train it, but we do not have other approach to solve this obstacle. So let's just try to train with more data to see what would happen. This is the training loss. And you can find that the loss do not decrease for a very long time. The loss stuck for 2 days. Before we are going to give up, suddenly the loss decreased. And we train the model for 1 week. Then we get the result of this green bar. So you can find that with more data, multilingual bird can learn the alignment, can learn how to do multilingual. So it looks like training data is very critical for alignment. If you do not have sufficient data, your model cannot learn how to align different languages. But on the other hand, I'm also worried that is it possible that data dominate the whole effect? Because in the past, actually, before people know pre-training, before people know bird, in the day that people only know water vac and glove, I know some people already try to put different language together and train water vac or glove model to see whether we can achieve multilingual alignment. In the past, no one say they can achieve multilingual alignment with water vac and glove. So I also try to train water vac and glove with 1 million sentences from each language to see whether they can learn how to do the alignment. The result is, even though they have the same amount of data as bird, even though water vac and glove have the same amount of data as bird, they do not work as well as bird. So it looks like there are 2 factors to achieve this kind of cross-language alignment. One is you need sufficient data. The other is you still need the bird architecture. You still need a large architecture to achieve that. Here we have some questions. No. Here's a question that do you use more data than the original Amber? I believe no, because Google have much more data and computing resources than us. We just say originally we use 20,000 sentences to train our own bird. Then we say, how about we increase to 1 million? But we still use less data than Google's bird. Someone asked, what's the intuition? Why did your loss suddenly decrease after 2 days? The answer is, I don't know. We should, I do not really have a good intuition here. Probably the only thing I learned is we have to believe deep learning more. So then the next question is how alignment happen? A typical answer is because different language share the common token. So model can learn the cross-language alignment. However, this cannot explain how Chinese and English can align together. Chinese and English, they do not share common token. One answer is probably in the Chinese data, you have some code switching. So code switching means in a sentence, you have 2 different languages. So in Chinese, even though Chinese characters do not overlap with English token, in the Chinese sentence, there are some English token, or at least you have some digits, or at least you have some punctuation. So different language, they more or less share some common token. So this is how multilingual bird align the token with the same meaning from different languages. Another explanation is because multilingual bird is trained by a large amount of different languages. So even though Chinese and English do not share common token, there is a language X. Language X has common token with Chinese and have some common token with English. And this language X is the intermediate language to bring the Chinese and English together. So this is some typical answer to try to explain why alignment happened. However, if you read this paper, its result will blow your mind. this paper say they have English data, then they generate a fake English, and they guarantee that in English and fake English, they do not share any common token. They do not share even punctuation. So there's nothing the same in English and fake English. Then they put English and fake English together to train a bilingual multilingual bird. Then they train their model, then they fine-tune their pre-trained model on fake English data and test on fake English data and get accuracy like 78%. Then if they train on fake English data, then evaluate on real English data, they get 77.5%, which is very close to the result of fake English. So they show that cross-lingual alignment is not necessarily come from common token. There are other mechanisms to achieve cross-lingual alignment. But what the mechanism is something still under investigation. Does that mean special distribution of embedding of different languages need to be rotated to match each other? Because in general, common concepts are closer together than different concepts. Yes, I agree with your idea. I also think in this way. So probably different languages, their distribution are very similar. And one language, you do the rotation, it can be mapped to another language. But there's still some unanswered question. I wondering, you know, the two languages, their distribution cannot be exactly the same. In this case, in fake English and English, their distribution are exactly the same. So probably it's very easy to learn the alignment. But what if they have a little bit different? And how large, when we have large difference, can we still learn the alignment? How large difference will prevent us from learning the alignment? I do not know the answer at this moment. This is a very good research topic. If you want to do more analysis about multilingual bird. Can this be because the models are learning the underlying structure of language in general? Yes, I agree with Manish. There probably an underlying structure in language and multilingual bird learned it, but this is a very good research direction. So probably we can do more, you can do more analysis like what are the languages share the common structure? Does all the language share the common structure? Does all the language can align to each other, or only some of them can align to each other? Here we have a question. Is the ability to encode different embedding for the same word based on the context of words surrounding it known as equivariant? This is probably a good question, but sorry, I do not really know the answer. I'm sorry about that. If other people know what is the definition of equivariance in natural language is, please feel free to type in the chat room so we can learn what is equivariant here. Oh, how to define NLI or NER label in fake languages, Actually, this is very simple, simpler than you expected. So what they actually do is you have an English NLI corpus and you already have the label. So for each English token, they map it to another token, which is definitely not appear in English. That's it. So the two language, English and fake English, they have exactly the same token distribution, but exactly completely different set of tokens. I hope this answers your question. Okay, let's move forward. Oh, it's already, I only have 30 minutes left. Okay, so, but the result is kind of weird to me because when you train the multilingual bird, lots of people say the language information is removed by multilingual bird. But I think it's impossible because when you train the multilingual bird, you input English and it just output English. It never output other languages. And you input Chinese, just input Chinese. It will not output other languages. That means multilingual bird do not completely remove the language information. It still know what language is for the input sentence. If it is completely language independent, if multilingual bird do not have language information, it cannot reconstruct the sentence properly. So I think the language information is in the multilingual bird embedding, but where it is. Then one student say, probably the language information is simply the average of the token in the same language. Means you simply take the token of, you simply take all the English token and average their embedding. This represent English. And you take all the Chinese token, average their embedding, then this is Chinese. And if the average, we find the representation of English and representation of Chinese, we can do something like that. We compute the difference between English average and Chinese average and obtain this blue vector. And multilingual bird take English as input, then we add this blue vector on top of the embedding. And originally the input is English, so it output English embedding. And this blue vector represents the difference between English and Chinese. So when we add this blue vector, can we transform an English sentence into a Chinese sentence? This sounds pretty crazy, but it works anyway. So it works a little bit. This is something very surprising. So the input sentence is, there is no one who can help me. So this is the input sentence. Then we add this embedding to a specific layer. Actually, we found that we can add this, that we can transform all the different layers and obtain the same phenomenon. And all the token is added by the same embedding. So we just shift all the embedding to a specific direction. All the embedding are shift to the same direction. Then the input is, there's no one who can help me. The output is, if you can read Chinese, you can understand what I'm talking about. The output is, there 是无人人 can help 我. And 我 is the Chinese character of me. And here 是 is the Chinese character of is. And 无人 is the Chinese character of no one. So it can do unsupervised token level translation in this way. Although the translation quality is kind of poor, but it truly do translation a little bit by simply add an embedding to each token. And this is not a coincidence. Only this is not on this phenomenon can not only apply on English and Chinese language pair. We tried 12 different language pair, and we observe the same phenomenon on all the language pairs we tried. So it looks like multilingual bird still contain the language information, and you can modify its latent representation a little bit. So input one language and output another language. Lots of people also have the same finding at the same time. Oh, so what is the meaning of the number here? So for convert rate means how many token is transform from one language to another language. And we do not consider accuracy here. So you can find that it is very easy to transform from one language token to another language token. So that means English tokens are in a region, and you just shift their embed into one direction, then they all corresponding to Chinese token. But the accuracy is not very good. Here we show the blue score. Okay, blue score is one way to evaluate how good your translation model is. And here the blue score are something around 10. So it's actually pretty poor, but it's not 0. So machine truly learns some translation, but only a little bit. I hope this answers your question. You may ask, what do we learn from this observation? How can we apply this observation? I do not really have a good answer. It's just an observation, but you can read this paper to learn more about we try to leverage this observation. Why is English to Germany worse than English to Chinese, even though? Yes, this is a very good question. The simple answer is I don't know. Reviewer also asked the same question, but we do not really have a good answer. I don't know why English and Chinese really have a very good result here, but English and Germany, we do not get a good result, but I do not have the answer. O1 translation, maybe this can be served as a, I do not really know what is O1 translation. Yeah, but this is one way you can do unsupervised translation because we do not really need any label data, but it's just token level translation as opposed to the usual translation. Okay, yeah, this can be one way to do translation, but because the performance is so poor and there are already lots of paper report good result on unsupervised translation. So if we say this technique can be used in translation, unsupervised translation, I believe a reviewer will not happy about it. Okay, so we only have 5 minutes left, but there's one very important topic I also want to share with you. This topic is about cross-discipline. This is something I also really want to share with you. So let me directly describe the experiment here. We apply BERT on other tests completely unrelated to language. So we apply BERT on protein classification, DNA classification, and music classification. And what do I mean by DNA classification? The data I obtain is something like that. So each DNA is a sequence of characters. We have 4 types of character, A, T, and C, and G, 4 types of token. And each sequence belongs to a class. Some sequence belong to EI, some sequence belong to IE, some belong to N. I don't really know what those labels mean. But anyway, just consider it as a typical sequence classification and just train your model. Then we leverage the English BERT on this test. So the idea is like this. You have DNA sequence. There are 4 types of token. We map each token to an English word. So A map to we, T map to you, and C map to he, G map to she. So a DNA sequence become an English word sequence. Then a BERT model take the English word sequence as input and let's do classification. Keep in mind that the BERT is pre-trained, but it is not pre-trained on DNA sequence. It is the BERT pre-trained on English. Let's see how's the result for those BERT pre-trained on English. So here is the result. We try several different tests. Here we try 3 protein classification tests. We try 4 DNA tests. We try 1 test related to music. And if you do not pre-train your model, the result in the blue box is the accuracy you obtain. If you pre-train your model, the result in the red box is the result you obtain. You can find that bird actually obtain pretty good result. Bird outperform those model trained from scratch, even though it's pre-trained simply on English, nothing about DNA. I know you feel very surprised. And this is not coincidence. I have to tell you that it doesn't matter which pre-trained model you use. We try Roberta, it works. We try Albert, it works. We try Chinese version of bird, it works. And it doesn't matter you map ATCG, the 4 types of token in DNA, to which English word. We have random tried several different sets of English word, and it performs similarly. So this is something very surprising. Then I also wondering why the English pre-trained bird can obtain good result on this test. Because it improved the optimization or it improved the generalization. Due to time limitation, let's do not go through the detail. I directly tell you the conclusion. It improved both the optimization and the generalization. So with the English pre-trained bird, the optimization becomes easier on DNA sequence. And even though optimization is not an issue, the generalization capability of English bird is better than trained from scratch on DNA sequence. And we also try another experiment. We consider that if trained on English data can apply on DNA, probably this means training data is not that important. How about we generate some artificial data? Then we pre-train on artificial data. We have a bird pre-trained on artificial data. Then we apply this bird on natural language processing downstream test to see what would happen. And we can generate different artificial data so we can study the characteristic between the data and the result on downstream tests. So the first observation is if we generate our data just randomly, our pre-trained data is something just random. It is as worse as trained from scratch. Because at the beginning, I'm thinking about probably pre-training is the key. The data is not important. You do pre-training on any kind of data, you can always get good result. So this probably explains why you can train on English and apply on DNA sequence, because data is not important. The pre-training mechanism is probably the key. But the experimental result here verifies that the data is still important. If your data is random, even though you train your bird model, it's as worse as train from scratch. So data is still important. But what kind of characteristic is important for the data? So one possibility is, as you know, language has some specific structure. Language has grammar. How about we generate a token based on some specific grammar? Then if you generate your artificial data based on some specific grammar, it works pretty well. The performance will be as good as pre-trained on non-English language. So if you train on another language and apply on the English downstream task, then train from those artificial data generated by some specific grammar, then the performance is as good as trained on non-English data. However, and also consider that is structure the key? Probably is other factor influence the result. So we do another experiment. We have a token sequence like that. It's simply 1 to 64. Then we randomly permute the token. So we randomly permute its order. Then we match some token, and the model have to predict the match token. To correctly answer the question, what model have to do is go through the whole sequence and take a look at what is the missing token. But this sequence do not have any grammar. It do not have some specific structure. If we train our model in this way, if we train our pre-trained model with this kind of artificial data, we get the performance as good as non-English data. So it looks like the structure is not the key. Probably make the model go through the whole utterance is the key. So if during the pre-training time, we can make the model go through the whole utterance, this is why it can obtain good performance on downstream tests. But however, there's one thing I have to mention. Although I say we can get the performance as good as non-English language, if you want to consider English downstream tests, training directly on the English always give you the best performance. We never create artificial data set that can be as good as English on the English downstream tests. So this is some surprise finding, but due to time limitation, I know we have to stop it here.